Okay, so I thought I'd make a video solution here for chapter 30, number 39. And let me just make a comment about this one. You'll see it when I explain the exam. But 39, as well as number 43, 45, 65, and 66 are really good and kind of a different and challenging, or at least 65 and 66 are challenging ones. But these other three, 39, 43, and 45, really are part of chapter 30, but they're the part that I'm going to say, let's hold off and do as we get ready for the next chapter. So I'm going to do 39 anyways, because a few of you are asking about it, but I do want to say, don't stress about this one. This one has to do with magnetic flux. Magnetic flux is just like electrical flux, but it's only useful when we get into the next chapter with Faraday's law. So we've got some pretty hard stuff already, and so the test is going to stop at section 4 in chapter 30, so it'd be, chapter 30, sections 1, 2, 3, and 4. This is the section on flux and Gauss's law of magnetism. But let me just do it and worry about the flux then after the exam here. So here's the question. It says a cube of length 2.5 centimeters is positioned as shown, and a uniform magnetic field is given by this equation. All right, so we have this cube. And the cube, I guess, looks something like this. And they do the vertical back edge as the y-axis, and across the back edge on the bottom of the cube as the x-axis, and coming out of the paper as the z-axis. And then they say there is this uniform magnetic field. And fortunately, they give it to us in components, because components make it actually a little easier to do. And they say it is 5 units in the x direction, and 4 units in the j direction, and the 3 units in the k direction. All right. Now, A says, calculate the magnetic flux through the shaded region. Now, the shaded region is this little face right here. So it would be, I guess, what I would call the right-hand side of the cube. But this will give me a chance to remind you about the definition of flux. We haven't really done it yet. Even in the lectures, I've kind of held it off till we get started into chapter 31. I would say, maybe I'll come back over here and say we did do electrical flux. And you might recall then that Gauss pointed out that if you were to calculate all the electrical flux on a closed surface, that would equal to the charge inside of that closed surface over epsilon naught, the permittivity of free space. That is definitely true. And the reason we focused a lot of attention on it in chapter 24 is it gave us a nice little tool for calculating the electric field. And so Gauss's law of electricity was really, really powerful. And we could do the same thing with magnetic flux. We can define it this way. And Gauss did. And Gauss even then asked the question, what would happen if you did the flux around a closed surface? And his logic being the same as he did for the electric field is to come up with this answer that, well, you'd always get 0. There is no monopoles. There is no individual piece. And in fact, this is a good way to do part B of this problem first. It says, what is the total flux through all 6 faces? Well, 0. All 6 faces would make a closed surface. And this is saying that the magnetic flux through any closed surface, whether it be a cube or a sphere or anything else, is going to be 0. So that's kind of what this problem is about. And it's also trying to point out that, we need magnetic flux, really for Faraday's law. This right here is called Gauss's law of magnetism, and it's really kind of boring. it can be useful at some times, but it always comes out to be 0 if you have a closed surface. Now, for part A, we don't have a closed surface. We just have one face. And so I want to take this integral and move it down here and actually do a calculation here on an A. But truth be told, the point of this problem is just to really point out that a cube is a closed surface and you get 0. And so we just don't have the same type of process for magnetic fields as we do for electric fields. So I'll say it again. This is the definition of magnetic flux. That's the point of this. And I haven't really emphasized magnetic flux purposely because it is going to come into play. And we are going to need magnetic flux on a non-closed surface. So that's Faraday's law coming up. But on a closed surface, which your author brings up in this chapter with Gauss's law, you always get 0. And there's really not much we do with it because it always comes out to be 0. And so it's not as useful as Gauss's law of electricity. All right. So there's the answer to B. That's the easy one. Now the answer to A is really more of take a dot product. And so I'll write the magnetic field. Oh, I don't know why I didn't put a plus there. As a vector. And then dot it into this area vector. Now, this area vector would be the magnitude of the area vector, and its direction is perpendicular to its surface, and so that's the I hat direction. And, of course, using the dot product of components, I dot I is 1, and so this is just 5 times dA. Whereas the J dot I is 0 and the K dot I is 0. So this is simply then just 5 times the integral of the area. And as I said a number of other times, let's not actually do this integral. Let's read it. And this is just saying add up all the little pieces that make up this face. And so if you would do that, you would get the total area of that face. And I didn't put it here in the picture, but the earlier part of this said this is a cube that has a height of L, a width of L, and a depth of L. So the area would just be L squared. And of course, L was, what was this, 2.5 centimeters. Let me write it as 0.025 and square it. And so now grabbing a calculator, 5 times 0.025 and square it comes out to be 0.003125. And the magnetic field is in Tesla, and area is in square meters. So there's the flux there. All right, that's it.